Hello students, today we are going to see about transient analysis. In last class we have seen about the introduction about transient analysis. We are going to see in elaborate in this class. Before going to that, we need to know what is steady state analysis and the transient analysis. So in steady state, the current voltage and frequency will be constant. In transient state, it will vary. Depending on the excitation, it will vary. Okay, so the behavior will change from one state. If the state is changing, for an example, the state is changing from on state to off state or off state to on state, the transient will happen. Okay, so this is called transient analysis. Then transient time means the transient takes place from one state to another state is called transition. Okay, so the transition takes place from one state to another state. So the time taken from one state to another state is called a transient time. Okay, the time taken for the circuit to change from one steady state to another steady state is called the transient time. So this is called transient time. We will see elaborate. uh, Next we are going to see about transient response of RL circuits. In RL circuits we are going to see in these sections, depending upon the excitation, we are going to see if the excitation is step signal, then impulse signal, exponential source and sinusoidal excitation. So depending on these excitations we are going to see the analysis. First we are going to see excitation by step signal. Consider this RL circuit. So we are having R and L in this circuit excited by a E of t source. So E of t is a DC source. Then we have connected the switch in series with that. Assume that the current is I. It is a series circuit, so the current will be same. So small I will be the current. Then voltage across resistance will be VR. Then voltage across inductance will be excuse me. The voltage across inductance will be VL. Okay. If we are applying KVL for this circuit, the potential rise is E of t. Then potential drop will be VR and VL. So VR plus VL. So KVL equation will be E of t equal to VR plus VL. Okay. We know that in DC source there will be a constant voltage, right? So that constant voltage will be V. So constant step input from 0 state to on state. So that is step. Okay. So E of t equal to V. Then voltage drop across resistance will be current into resistance. So I into R. Then voltage drop across inductance will be L into di by dt. So VL equal to L into di by dt. If we substitute these values in this equation, we will have V equal to I into R plus L into di by dt. Okay. This is the differential equation for this circuit. We can see that this equation is a first order differential equation. So this circuit is a first order circuit. Okay. Then for solving this equation, in last class we have seen the differential equation. By integrating we have solved the equation. In this class we are going to see the Laplace transformation technique. We are going to apply Laplace transform for this equation on both sides. Okay, we are going to apply Laplace transform on both sides. If you apply Laplace transform I into R, here R is the constant value, I is the time domain value, I of t. Okay, R into I of t. So R will be constant, I of t will be converted as I of s. Okay, time domain will be converted into S domain. Then L is constant, dA by dt. We are going to take Laplace transform for for this differential equation. So L into di by dt, for differential equation we will add s into ifs. Okay, so s into ifs, I of t, for I of t Laplace transform will be ifs, then minus I of 0. I of 0 is the initial state. Initially the current will be 0, right? Before switching on this switch, the current is 0, so I of 0 is 0. Okay, so the I of 0 will be 0 here. Then the v is the constant, so v by s, Laplace transform for constant is 1 by s, so v into 1 by s. Then if we simplify this equation, the I of 0 will be 0, so R into I of s plus L into s into I of s equal to v by s. Okay, then we are taking I of s in common, so I of s into R plus L into s equal to v by s. Then I of s equal to v by s into R plus s into L. So for solving this equation, we are taking a partial fraction. If we take partial fraction for this portion, b by s into R plus sl equal to a by s plus b by R plus sl. So this is the partial fraction for this equation. Then if we simplify this equation, we will get b equal to a into R plus sl plus b into s. Okay, so b and a are constants. We have to find a and b. For finding a, we need to eliminate this part, so substituting s equal to 0. If we substitute s equal to 0, we will get, so this part will be cancelled, so a into r into v, sorry, v equal to a into r we will get, then a equal to v by r. Okay, then we want to find b value. For that we need to cancel this part, so r plus sl should be equal to 0. If we substitute r plus sl equal to 0, we will get s equal to minus r by l, right? So let's substitute s equal to r by l. If we substitute s equal to r by l, sorry, minus r by l, this part will be cancelled. Then v equal to minus b into r by l. Then b equal to minus v into l by r. So we will get a and b value by substituting s equal to 0 and s equal to minus r by l. Okay, now substitute a and b values in equation number 4. So we will get this equation. After simplifying this equation, we will get this. In these two terms, we are having v by r in common. So take v by r in common. Then 1 by s minus l by r plus sl. Okay, so here we are taking l as common. So if we take l as common, s plus r by l. So in this term we are having s plus r by l. So l and l will be cancelled. Then I of s equal to v by r into 1 by s minus 1 by s plus r by l. Okay, so this equation will be 5. Then so this domain will be in s domain. We are converting this s domain equation into t domain, time domain. For that we need to take inverse Laplace transform. So take inverse Laplace transform on both sides. If we take inverse Laplace transform, L inverse of I of s equal to v by r is constant, so v by r. So this is the summation. So L inverse of I 1 by s minus L inverse of 1 by s plus r by l. Okay, L inverse means inverse Laplace. Then inverse Laplace for I of s is I of t. Then inverse Laplace for 1 by s is 1. So initially we have seen for constant the Laplace transform will be 1 by s. So for that inverse Laplace will be 1. Then minus L inverse of 1 by s plus r by l. So s plus a, if we take 1 by s plus a, that will be in e power minus a into t. That is the inverse Laplace transform for that equation. So in that term a, we are having r by l. So e power minus r by l into t. Okay. So this is the transient current equation for RL circuit. Okay. So we need to know the final value. For finding the final value, we need to substitute time as infinity. If we substitute time as infinity, we will have, so if e power infinity equal to minus 1, so minus, sorry, if we substitute time equal to infinity, we will have v by r as the value. Then I of t at time t equal to infinity will be equal to v by r. Okay, so this is the steady state current. If we draw characteristics for this equation, we will have this graph. So we are taking time as x-axis and I of t as y-axis. If we draw characteristics, we will have like this. Exponentially the current will increase, so exponential equation we will have the steady state current is v by r. So at time t equal to infinity, the current will be v by r, so it is v by r steady state current. So this part is a transient state. Okay, this part is transient state. After this time the current is constant, so it is steady state. Okay, so up to this the time is steady state, sorry, transient time. After that this is the steady state. Okay, so steady state, and this part is the transient state. Okay, now you can understand the transient state and transient state. Okay, steady state, this one is steady state, and this one is transient state. Okay, so at any time t1, the equation will be like this. Then consider tau is L by R. This equation we have seen in the last lecture also. If we substitute tau equal to L by R, this equation becomes I of t equal to V by R into 1 minus e power minus t by tau. Okay, this equation will become like that. Then substitute this tau equation here. So if we substitute this, we will arrive v by r into 1 minus e power minus 1. Okay, so e power minus 1 is 0.3678. So if we substitute in this equation, we will have I of t equal to 0.632 into v by r. 0.632 is 63.2 percentage. So this equation implies that 63.2 percentage of steady state or final value. Okay, so v by r is the final value here. Okay, at time t equal to L by r, 63.2 percentage of the current will be applied in the circuit. Okay, this is the explanation for this equation. Okay, at time t equal to L by r, 63 percentage of final value will be achieved. Okay, then so tau is the time constant. This is the definition for time constant in RL series circuit. Okay, so the time constant of an RL series circuit is defined as the time during which the current increases to 63.2 percentage of its steady state value. Okay, so this is the time constant definition for RL series circuit. Okay, so nearly 63.2 percentage means it will come around here. Okay, so at time t equal to L by R, okay, the current will be 63 percentage of V by R. Okay, then last part of this derivation. So if they ask to derive transient current equation, you can stop here. Then draw these characteristics. If they ask the value of final steady state value, then derive up to this. Okay, if specifically the question is asked for to derive the transient voltage across resistor and inductor, you can write, otherwise you cannot write this part. Okay, so transient voltage across resistor and inductor. The transient voltage across the resistor will be VR. So VR equal to I into R, we know. Okay. So substitute I of t value here. So V by R into 1 minus e power minus R by L into t. So this is the I value into R. Here R and R will be cancelled. So VR equal to V into 1 minus e power minus R by L into t. So this is the transient voltage across resistance. Then transient voltage across inductor will be VL equal to L into di by dt. So substitute I of t here. So L into di by dt into V by R 1 minus e power minus R by L into t. V by R is constant, so take out. Differentiate this equation. Differentiation of 1 will be 0. Then differentiation of e power t is e power t. So e power minus R by L into t. Then differentiate minus R by L into t here. So if we differentiate, we will have minus R by L. So R into R cancel, L into L cancel, minus into minus plus. So V into e power minus R by L into t. So this is the voltage, transient voltage across inductor. Okay. So these are the today's portion. So this is the transient response of RL circuit. Okay. If you have any doubts, please comment. Okay. Thank you for listening.